Black holes are among the most fascinating and mysterious phenomena in the universe. These cosmic giants wield immense power, yet remain practically invisible to us. A black hole, perhaps 2 to 4 times the mass of the Sun, is so dense that its gravitational pull allows nothing, not even light, to escape. Thanks to decades of research, we've progressed from knowing almost nothing about black holes to uncovering increasingly detailed insights into their nature. Recently, groundbreaking discoveries have shed light on what lies within a black hole, offering new perspectives on these enigmatic structures. The origins of black hole research. The concept of black holes was first proposed in 1916 when Albert Einstein published his theory of general relativity, which predicted their existence. At the time, black holes were purely theoretical. It wasn't until the 1960s that scientists found tangible evidence of their existence. While studying the Cygnus constellation, astronomers observed a bright blue star emitting X-rays in a peculiar pattern. Further investigation revealed these X-rays were being drawn into a massive, unseen object, a black hole. This discovery, Cygnus X1, provided the first evidence that black holes were not merely a figment of Einstein's imagination. Situated roughly 6,000 light-years from Earth, Cygnus X1 is incredibly dense and shines tens of thousands of times brighter than the Sun, its powerful gravitational pull capturing everything that ventures too close. The nature of black holes. Black holes are areas in space where gravity is so strong that nothing, not even light, can escape. Any matter approaching too close is pulled in and compressed into a singularity, a point of infinite density. Despite their fearsome reputation, they have become a crucial subject of scientific investigation. One of the most intriguing and terrifying properties of black holes is their effect on objects that fall into them. A phenomenon called spaghettification occurs, where the immense gravitational forces stretch matter into thin, elongated strands before it's consumed. Despite these dangers, black holes are relatively far from Earth, with the nearest estimated to be 500 to 1,000 light-years away. A groundbreaking image. In 2021, scientists captured the first clear image of a black hole, the supermassive black hole at the center of the galaxy M87. This achievement involved stitching together multiple images over several nights to create a composite. The result revealed that black holes are not merely empty voids but consist of 3 distinct layers. The event horizon, the point of no return. Anything crossing this boundary is irrevocably drawn into the black hole. The photon sphere, a region where light orbits the black hole, trapped by its immense gravity. The singularity, the core of the black hole where matter is compressed into infinite density, and the laws of physics as we know them cease to apply. The challenges of studying black holes. Black holes are exceptionally difficult to study directly. Their gravitational pull ensures that anything crossing the event horizon is irretrievably lost, making it impossible to send probes or gather direct data. Instead, scientists rely on indirect observations, such as analyzing the radiation emitted by matter as it approaches the black hole or studying the behavior of nearby stars and gas. Adding to the challenge, no 2 black holes are alike. While they share the same basic structure, their behavior and characteristics can vary significantly. This uniqueness, combined with the breakdown of known physical laws at the singularity, makes black holes one of the most complex objects to study in the universe. The formation of black holes. One widely accepted theory of black hole formation involves the collapse of massive stars. When a star exhausts its nuclear fuel, it can no longer counteract the inward pull of gravity. If the star is massive enough, this collapse continues until it forms a singularity. The future of black hole research. Despite the challenges, scientists continue to develop innovative ways to study black holes, from advanced telescopes to sophisticated simulations. These efforts aim to unravel their mysteries, shedding light on fundamental questions about the nature of space, time, and gravity. Black holes remain one of the most compelling frontiers in astrophysics, offering a unique window into the workings of the universe. Each new discovery brings us closer to understanding these cosmic enigmas and their role in shaping the cosmos. Researchers have focused their efforts on the center of the universe, particularly on the galaxy M87, where stargazers observed a powerful whirlpool of intensely hot hydrogen gas rotating at an astonishing speed of 1.2 million meters per hour. Despite the immense energy of this spinning disk, which should have caused it to violently fly apart, it remained intact. Scientists concluded that an immense gravitational force must be holding it together, suggesting the presence of a massive object at the galaxy's core. This object, estimated to have a mass of 2 to 3 billion suns, was identified as a black hole. However, black holes are not limited to this explanation alone. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations of gravity to provide a groundbreaking description of a spinning black hole. Kerr theorized that instead of collapsing into a singularity, a rotating black hole would form a ring-like structure or a thin disk. The incredible rotational forces would prevent the matter from collapsing further. This spinning region, known as the ergosphere, surrounds the black hole and marks the area where the laws of physics begin to break down. One of the most fascinating implications of Kerr's solution was the theoretical existence of an Einstein-Rosen bridge, also known as a wormhole. A wormhole is a hypothetical passage through spacetime that connects two distant regions of the universe, or even parallel universes. According to this theory, if someone were to fall into a black hole, instead of being crushed into oblivion, they might travel through a tunnel formed by the ring of rotating matter and emerge from a white hole in a parallel universe. To understand this concept, we need to revisit the nature of spacetime as described by Einstein's theory. In this framework, objects with mass bend the fabric of spacetime, creating a gravitational field that pulls other objects toward them. Imagine spacetime as a flat sheet of paper. If you draw 2 points on the paper and connect them with a line, this represents the conventional path through spacetime. But what if you could fold the paper and create a shortcut between the 2 points? This is the essence of a wormhole, a shortcut through spacetime. Although wormholes have been a popular subject in science fiction, they are also a prediction of general relativity. However, no one has directly observed a wormhole, as they are inherently unstable and would collapse almost instantly. If Einstein-Rosen bridges exist, they would suggest that black holes are not merely cosmic vacuum cleaners but could also serve as gateways to other regions of spacetime. Could we use wormholes for space or time travel? Unfortunately, the answer is likely no, at least for now. Even if a wormhole could be stabilized, it's improbable that it would allow travel faster than the speed of light. According to Einstein's theory of special relativity, the speed of light is the ultimate limit for anything moving through spacetime. Still, the idea of wormholes as pathways to other parts of the universe, or even to different times, remains a tantalizing subject of research and speculation. The most intriguing type of wormhole, based on Kerr's work, is called a Kerr wormhole. This theoretical structure could connect two distant points, such as different universes or even separate times within the same universe. Kerr wormholes are often depicted as ring-shaped portals, similar to the mirror in Alice in Wonderland. Just as Alice stepped through the looking glass into a world where logic and rules were different, passing through a Kerr wormhole might transport a traveler to a completely different universe or era where the laws of physics are unfamiliar. While the concept of wormholes as a means of interstellar travel or time travel is exciting, it remains highly controversial. Critics argue that wormholes, especially Kerr wormholes, are unstable and potentially impassable due to the intense radiation and subatomic forces surrounding their entrances. Einstein's equations of gravity, which describe wormholes and black holes, apply only to gravity and not to the quantum forces that govern radiation and subatomic particles. To fully understand these phenomena, a new theory is needed to unify the laws of gravity with quantum mechanics, what physicists refer to as a theory of everything. One promising candidate for such a theory is string theory, which Michio Kaku and other physicists have been exploring for decades. String theory suggests that subatomic particles are not point-like dots but tiny vibrating strings. These strings, like notes on a violin, vibrate at different frequencies to produce different particles. According to string theory, the vibrations of these strings distort the fabric of spacetime, creating phenomena like black holes, wormholes, and other exotic solutions to Einstein's equations. Fascinatingly, string theory requires 10 dimensions of spacetime, far more than the 3 dimensions of space and 1 of time that we experience in our daily lives. These additional dimensions are difficult to visualize, but physicists have proposed models to help us understand. For instance, imagine a two-dimensional lake inhabited by fish that are only aware of length and width. To these fish, the concept of height does not exist. Similarly, the extra dimensions predicted by string theory may exist beyond our perception but still influence the universe. In essence, string theory not only bridges Einstein's theory of gravity with quantum mechanics but also offers explanations for some of the universe's most mysterious phenomena. However, much remains to be discovered and understood before theories about wormholes, alternate universes, or time travel move from science fiction to scientific fact.